All right, so we're on April 15th, and Monday you had test 3. That is your last test for the semester. So now we're just doing kind of like full semester review. So we're gonna finish up stacks and queues and all that stuff so that you'll be ready for the final. But then we're gonna just kind of go through some of the harder topics of the class, make sure that those are ironed out. And then next week is PA workshop. So any of your programming assignments that you have trouble with or are still working on, you can use that time to ask me questions and I can go through those with you, okay? So let's go ahead and just finish up. I'm gonna go through 202. So we went through these slides. I'm just gonna make sure that there's nothing and then that I want to cover. One thing I am going to cover is Java comparators. I'm going to show kind of how they work. And then we'll talk a little bit about stacks and queues a little bit more, but we've already talked about those. And then hopefully next class we can start doing a little bit more review stuff. So this looks like everything that I've had. Okay, so let me see if I can show you some comparator examples. Sure. There we go. Okay. So there's a couple of different ones. So let's do this guy here. Okay. So much like the comparable interface is something that you implement within the object itself. So let me kind of give you another example, comparable. So let's see if I can split vertically. There we go. Okay, so here is kind of the two examples side by side. So in the right here is what you've done before. So here is the comparable interface. And the comparable interface is something that gives a different type to the element itself, okay, or to the object itself. So it's not outside of the object, it's actually embedded and it adds a new type. So employee is not only of type employee, but it's also of type comparable. And so you only have one argument here. And what that allows you to do, and this is a terrible implementation of a compare to method, but what it does is allows you to compare yourself, employee, to another employee object, okay? So that allows things like collections.sort, they take type comparable and allow within the list to compare yourself to other objects of the same type so that it knows how to do sorting and those type of things, okay? So that is the comparable interface. That's what we've done so far. The comparator interface is a completely different object that exists outside of yourself. So if you wanted to compare geometric objects, you would create a completely different class. You see this is geometric object comparator, and it implements the comparator interface of geometric type. And then this allows you to compare the two objects outside of themselves. And so the comparator implementation is actually what you use for priority queues. So whenever you create a priority queue, it will ask for an initial size when you call that constructor or something like that. But the final argument is, hey, give me a comparator so that I can determine which priorities bubble up to the top, which objects bubble up to the top. And that's what this is doing. So in the comparator implementation, you can then say, okay, between these two objects, if this area is less than the other one, I want it to become before it. If the areas are equal, then obviously return a 0 saying that they're equal. But if not, which would mean that area 2 is less than area 1, then return 1. I want the area 2 to come afterwards. Okay. So that's how the comparator works, is you would pass this into a priority queue, and then the priority queue would use this comparator and take 2 objects at a time, pass them into this comparator, and get some priority ordering and bubble the ones to the top that actually matter. Okay, so let's see if we can find an example priority queue of a priority queue. So here we go. All right, so this is just a simple little example using string. So priority queue of string, and we just put some states in there: Oklahoma, Indiana, Georgia, Texas. Okay. And so in this one, we say that we're using priority queue using comparable. Okay. Comparable. I don't know why it says comparable. Oh, I see. So what it's doing here is it's saying while q.1, that size, especially going through the entire list, this could be a for loop, and then it's just removing the top of the one from the list. Okay. So it's not really doing anything. So you should get the same order: Oklahoma, Indiana, Georgia, Texas. The second example is we're creating a priority queue of initial capacity of 4. We put the same objects in there, but then you see this final argument this is actually an existing comparator. Okay, this is one that Java provides, and it's called reverse order. It's a generic comparator, so you can pass any object into it, but basically what it does is it returns a comparator that will, no matter what objects you pass into it, it will reverse the order of the list. Okay, so whenever we print using this comparator, we would say it would come out Texas, Georgia, Indiana, Oklahoma. So let's just give it a try and see what happens. That's right. Here we go. It's some other bug. Okay, so this is what we get. So in the first instance, we get Georgia, Indiana, Oklahoma, Texas. Okay, so that ordering should be just alphabetical. Okay, now I see why they said using comparable. So I guess the default of the priority queue, if you do not pass a comparator, is the actual ascending order. So GIOT, that makes sense. Here's the one using comparator. So then you pop the off the bottom. So this is reversing it. Texas, Oklahoma, Indiana, Georgia. So this is also doing descending order, since reverse order would be flipping whatever. Okay. Didn't realize that it actually does by ascending order, but that's what makes more sense now. So the initial one, so I may have told you wrong, the initial one is based on ascending order. So using comparable, it would just be GIOT, Georgia, Indiana, Oklahoma, Texas. Passing the collections reverse order actually gives you the reverse order of what the normal priority queue would be, not the order in which you put the elements on the queue. And so that's why you get Texas, Oklahoma, Indiana, Georgia. And so this is how the priority queue works: is you can put elements on the queue in any order, and then they will be returned based on the comparator that you provide. Okay, so that's pros and cons. But the pro of that is that if you have your comparator written very well, then you know that the order that you're going to get is the order that that you desire. So priority queues I've used very not I haven't used that much. If there was any order that we wanted to make sure that we retrieved from the list, most of the time we would write something that ensured they were put on the queue or list in the order that we wanted to retrieve them. Very, very few times have we wanted the list or the data structure itself, such as a priority queue, to do the ordering for us. However, there's nothing wrong with this implementation, and it's actually a lot less code to do it this way. And then the only thing that you have to maintain would be some sort of comparator, and then your actual data structure implementation doesn't need to change. So there are pros and cons to both sides, but I've never used something like this. I wanted to show you this because I didn't get a chance to show you comparators before your previous test. So now on your final, I have to check, but I think there actually is an implementation for a comparator that you'll have to complete. All right, stacks and queues. So we've already went over stacks and queues a good bit, but we'll keep going through. So keep talking about the vector class. It was introduced early in Java. I mean, whenever I was introduced to Java, I hit Java at Java 5, and I think by then, even then, the vector class wasn't used much. So there were a couple ones, but that were used, and that was vector and stack class. And so then I think in Java 5 actually came out the whole new revamped Java collections framework, which was all new data structures and a whole new approach to data structures within the language. And so that's where the vector class was kind of redesigned to fit into that. But they still maintain some backwards compatibility based on the methods that were provided. But anyways, a vector is essentially, I'm pretty positive vector is like a queue. And then the stack class is the stack itself. But then they basically the vector class is the same as the array list. And then the vectors were for more synchronized access. So between synchronized and asynchronous access, that has to do with threading. So if you are doing different threads and you're accessing a data structure at the same time with multiple threads, you have to use some sort of thread safe data structure. I'm pretty sure that the vector class did not contain any kind of protection around thread safe. It was all synchronous actions to the data structure itself and not asynchronous. So you have to be careful with that. But I mean, like I said, this is an old school data structure. And then this was just the methods a part of the vector class. You can see it's very much the same as an array list. So instead of it, you had the add element. Capacity would be size. You could copy into an existing array. That would be the same thing as like add all that you'll see on the list interface. You can get an element at a certain index, get all elements. Ensure capacity. So the array list class, you can add, and you don't need to worry about what's the capacity of the data structure itself, because once you hit that limit on the back end, that array will be incremented and copied over into a new larger array for you. Vector was not the case. So you actually had these methods called what is my current capacity, and ensure capacity would increase the capacity of it. So you had to do a lot more overhead with it. Get the first element, you get insert element at a certain index. Remove all elements, remove an element of a certain object, remove an element at a certain index. And this is an example of overloading. Okay, just kind of going back into our class. You have the exact same method name, remove element, but completely different signature. So you have a different parameter, which is an object, and a different parameter here, which is an int, and actually returns two different things. So that is a perfect example of overloading. Set element. You could change an element at a certain index, set size, and then trim to size. So basically, trim to size would say, you would cut off, you would shrink the vector to the size of how many elements are in the vector at that time. Okay. All right, so then the stack class. So the stack class is LIFO. Okay, remember those two, LIFO, LIFO, and FIFO, FIFO. So stack, last in, first out, meaning it's like a stack of books or stack of anything. You put them on, you put them on, you want to get something off, pull the one off the top. It's like a stack. So the last one that was put on the stack is the first one to get taken out of the stack. Okay. They're removed from the top of the stack. You can retrieve, insert, and remove an element. Okay, so this is just some of the different methods, and remember these. So peek returns the top element, pop returns and removes the top element, and then push. So I remember, I think some of those were on your test. Just remember there's a couple of different ones: peek, pop, offer, push. So just remember the difference between those and the priority queues. A queue, priority queue, is first in, first out. And I would argue that the priority queue is the first in. The first out is the one that matches the criteria of your comparator. Okay, but a standard queue is first in, first out. Elements are appended to the end of the queue. Hang on 1 second. 1 second, sorry. I was looking at something right now. Okay. Oops. So queues, elements are appended to the end of the queue and removed from the beginning queue. We've talked about this. This is much like you're standing in line at a coffee shop or any other line. Whoever gets there first is the one that gets offered first, okay? There's actually there's a lot around queues, and that just kind of giving you a real world example of one. So one that is very, very used within industry is something called RabbitMQ. Okay, and so it is a message broker. Just kind of thinking of it. I'll try to explain it, but it's basically a queue. It is a queuing system. But imagine you have multiple applications that need to talk to one another, written in different programming languages, so C# and Node and Java and Python and whatever. And you need a way to talk to them. Well, you can all agree on a message structure. RabbitMQ is a message broker where you pop these messages on a queue, and you have someone who is a publisher to the queue and someone who is a subscriber to the queue. And as soon as the message gets put on the queue, the subscriber gets the message and then can do something with it. And so it is very much like a standard queue within any data structure or programming language. It is first in, first message on the queue is the first one to get consumed. Okay, and so that's what it does. You can look at this later, but this is something that is used very much within industry. In fact, I wrote an app just a couple of days ago and spun up a whole new RabbitMQ instance so we could do this between two different applications doing two completely different things, but needed a way to communicate to one another asynchronously. RESTful APIs allow it, but there is a synchronous aspect to it. Okay, so that's just a real world example of what queuing looks like in the real world. Okay, and then here is the messages for a particular queue, or excuse me, the methods for a queue interface. And there we go. So the first one being offer, and you saw that earlier. Offer is what it looks like to insert into the queue data structure. Poll retrieves and removes the queue, or null if the queue is empty. Remove retrieves and removes the queue, or throws an exception if the queue is empty. Peek retrieves but does not remove the queue, return null if the queue is empty. And element retrieves but does not remove and throws an exception. So you see there's four methods, kind of a permutation of what causes them to throw an exception or return null. And this is just a simple queue example. So it's the same example we looked at earlier, except instead of using a priority queue, we're using a queue. And offer is the method used to put elements on the stack. So with a standard queue implementation, this should be printed out in the exact opposite order. So we put in Oklahoma, Indiana, Georgia, Texas. It should print out, or excuse me, the same order. We get off Oklahoma, India, Georgia, Texas. Okay. If it was a stack, it would be the last. So it'd be Texas, Georgia, Indiana, Oklahoma. And then the priority queue class, we went through this as well. Initial capacity, a regular queue, or the one at the bottom, which allows you to set a specified capacity and the comparator, in which allows them to come to the top. And so this is the example that we looked at earlier. Okay. So just using a standard comparable, which returns them in ascending order, versus reverse order, which returns them in descending order. Okay. All right. And I think we got, make sure that there's no more slides. See if I can just start. We got a couple minutes left. Like I said, I've just been doing the short 30-minute classes. But let's just cover hash maps a little bit. Okay. So the main difference between a list and a map is that a map is two elements in one entry. It's like a key value pair. Okay. So it's basically key value. So the hash map, you can see how it's declared there. You can do, and it is in a generic type. Okay, key value. You can do any types, but this is how it looked like if you actually declared it. So imagine this is a map of the state population, where the key is the state. Let's say it's the state symbol like SC, NC, or ID, or any of those. And then the integer is actually the population. So in one data structure, you can have a key value mapping, and you don't have to have multiple data structures, or multiple aspects of data in one entry. You can have that within one data structure, where you can actually look up this data also by the key. So you can get, give me the value at this key, and you pass in SC. Okay, so let's just look at that. So you have the put method and the get. Put is the same as the offer or the push for the previous two data structures, but you're basically putting on the map an entry with two values. So this was looks like. So you would say, I want to put at the CA location, or at the CA key. This is the data. This is the population. And Arizona, this was the population. And then in Maryland, is that Maryland? I think so. This will be the population. Okay. And then after you have that data on the data structure, you can do state population.get, and then provide a key, and that will allow you to get that data off that map. And then I'll cover this, and then I'll just kind of go over this briefly and show an example next class. But putting a key value pair, this is what we talked about. Tom is 14 years old, and John is 86 years old, maybe a name to age. Put if absent. So what this does is it does a check first to see if the key exists in the data structure. So for example, if you run these two together, it won't put Tom is 20 on the list, because it already has that Tom 14 here. So this prevents you from overriding existing values, which is kind of a safe way to put data on the elements. And then this is how you get them all. So you pass in the key, and then it would return an actual integer. Okay. So we'll dig into this more next class, and I'll show you some examples of what that looks like. But that's all I have right now. Any questions? No questions. All right. Well, it's Wednesday. We'll go over. Let's look at the schedule real quick. We'll go over the rest of this and do just kind of some high level review of the whole course on Friday. Programming assignment workshop. We'll do that next week, and then that's that. I'll start talking about final exam and how to complete that, and we'll be done. All right. We're good to go. Have a great day. And that's all I have for you.